We know that in a circumstance like this, where we have a sort of a variable quantity squared set equal to a number, that we can use this taking square roots idea to say that, gee, if this unknown quantity squared is equal to 5, then this unknown quantity, which is being squared, is plus or minus the square root of 5. And then from there, we find x to be 4 plus or minus the square root of 5, our two solutions to the equation. Now, let's kind of move from this a little bit. Take this, which we already know, and let's expand it a little bit and see if we can come up with another technique of solution. You see, if we can create a situation where we have a binomial squared set equal to a number, then we can go through this solution. But we're not always faced with this situation. Example, suppose I go ahead and square this and work backwards a little bit. I'm going to expand and go up here. I wonder if we could recognize the situation if we had this. You see, could we go to this form and then down to this form? Maybe. And then if we were to put both all the terms on one side, that is, subtract 5 on both sides, then it would turn out that this would be unfactorable. So what we'd like to do is create a situation where we can take a relatively unfactorable trinomial, quadratic trinomial, and manipulate it into a form where we have a binomial squared set equal to a number, and then we can solve like this. All right, that's where we're going with this discussion. Now, the situation begins like this. It starts out by looking at a quadratic equation, investigating to see if it's factorable. No, it isn't. And then deciding to use a method, a manipulative method, where we're going to create a binomial squared set equal to a number. And here's how we start. We say, all right, let's take x squared minus 8x, these two terms, and let's leave them right here, and let's take this constant and kick it to the other side. Let's move it out. And we can move it out here by just subtracting 11 on both sides. So we'll get this. Now, our intention here is to invent a constant that we're going to add right here. Now, of course, if we add it over here, we have to add it on the other side to maintain balance in the equation, but we'll get to that in a little bit. It's the identification of this value that will allow us to factor in a certain way that we're driving at here. Now, we're trying to create a situation where we factor into a binomial squared. A trinomial which factors into a binomial squared is called a trinomial square. This is a perfect square trinomial because it factors into a binomial squared. And what we intend to do here is complete this trinomial square. And that's why this method is called completing the square. We are completing the trinomial square in order for the factoring to take place. Now, how do we do that? Well, we do it by noticing some characteristics of binomials squared and the resulting trinomial square. Now, I can just show this to you right quick and tell you how to do it from a manipulation standpoint, but I think it's kind of wise for us to understand this. Suppose I have x minus 5 squared, and I go ahead and expand this. I've got x squared minus 10x plus 25. Here's what I want you to notice. That if I take half of 10 and square it, I get 25. Half of 10 squared is 25, and that half of 10 is also right here. Half of 10 squared is 25. Now, watch this. I don't care if it's plus or minus. It doesn't make any difference. Squaring, I get x squared. Then here, now remember, when you square a binomial, you double this product. So, and that's all I'm doing here to create these trinomials. But I'm doubling 3x to get 6x, and then 3 squared is 9. Okay, great. Now, what I want us to notice is that half of this squared gives 9. You see, if we didn't know that there was to be a 9 there, the way to calculate it, or a way to calculate it, would be to take half of the 6 and then square that amount to get the 9. You see, we could invent that last term. We know what it is by knowing what this is. And that's the key to completing the square up here. We're trying to complete the trinomial square. And in order to do that, all we need to do is take half of the coefficient of this first degree term and square it. And that's what we're going to add right here. Half of the negative 8 is negative 4. Now, signs don't make any difference because whether we're thinking negative 8 or positive 8, when we square, we're going to get the square of the value anyway. So it's half of negative 8 plus or minus 4 squared is 16. So it's 16 that we're adding here. And if we add 16 on the left, we have to add 16 on the right to maintain the balance in the equation, and away we go with our solution. Now, the key to this whole thing, the key to completing the square, is to identify that value, that number, that completes the trinomial square. And then from there, it just kind of all drops out. Here's what happens. We go through a factoring process over here. This becomes, as expected, it becomes x minus 4 squared. Now, another nuance here, and I'll continue and go over to the right in just a minute, but I'm real excited about telling you about this. If we identify precisely what is being squared to give 16, then we're identifying this value. You see, what we're doing is we're adding, let's see, what did we add here? We added half of this squared. Half of negative 8 is negative 4 squared. And look at this, it's negative 4 right in here. So a lot of times you might want to leave this in a sort of a factored form here, but go ahead and expand it over on the right side. All right, so it just helps us with the factoring back. It's not a difficult process without doing this, but it's just a way to identify this other part of the binomial. All right, on the right, negative 11 plus 16, that would be 5. And now we're in a position where we were a little bit earlier when we solved this from this factored form. So if this amount squared is 5, then the amount is plus or minus the square root of 5, and x then is 4 plus or minus the square root of 5, our two solutions to the equation. All right, let's go through the process again. Here we have a situation, and the trinomial here is unfactorable. And so we're going to solve by completing the square. Now, I say it's unfactorable. We would investigate for that. All the signs are plus, so we would be thinking like this. Our first order of business is to try to factor. We would go through this. All signs are plus, 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 all the way across. Factors of 16 that add to give 12. Let's see, could it be 8, 2? No. Could it be 4, 4? No. Could it be 16, 1? No. So we go through all of that thought process. All right, once we get to that point, we say, aha, let's solve by completing the square. So to do that, we begin the process by taking the existing constant and kicking it out. We do that by eliminating it from this side. We see plus 16, we subtract 16 on both sides. So we get this. All right, now we want to complete the square. To complete the trinomial square, we take half of this and square it. Half of 12 is 6. 6 squared is 36, so we're adding 36 here. And we add 36 then on the other side. Now we can easily factor into x plus, now notice plus plus, so plus, now 36, 6 squared. You see, and again, we could have written this as 6 squared and identified the value that goes here. All right, on the right, we have negative 16 plus 36, that's 20. And now we go through in this process from this point of taking square roots. If this variable quantity squared is equal to 20, then this quantity must be plus or minus the square root of that. So that means x plus 6 must be plus or minus the square root of 20. And then we go through the gyrations of cleaning this up a little bit. Subtract 6 on both sides. We have, we have minus 6 plus or minus, and this has a 4 in it. It's 4 times 5, and the square root of 4 gives 2, so it's 2 the square root of 5. And these then are our two solutions. All the action, though, with completing the square is up here at the front end. Here's another one, and we would go through, again, the process of trying to factor, probably, unless the instructions say solve these equations by completing the square. And that a lot of times is what's going to happen in this situation. So to solve by completing the square, we would take the existing constant and kick it out. In this case, we're adding 14 on both sides, so we get this. Now we'd like to reinvent this constant. We reinvent the constant by taking half of the 4 and squaring. Half of 4 is 2. 2 squared is 4. So we're adding 4 here. We're adding 4 over here. And that's all there is to it. And when we go through the factoring process, the sign here will take on the sign of the middle term if we're confused about that. Another way to identify it is to identify precisely what was squared here to get the 4, but that's not a big deal either. So let's see, here it'd be x minus 2 squared equals 14 plus 4, that's 18. So x minus 2 then is plus or minus the square root of 18. And x then, adding 2 on both sides, we get 2 plus or minus, let's see, 18 has 9 in it, the square root of the 9 is 3, and then left under the radical is the leftover factor 2. Our two solutions. Here's another one. Now, the problems become difficult by virtue of the difficulty in manipulating arithmetically, taking half of the middle term and squaring it. And it's a little more difficult to take half of an odd number, you see. But it's the same idea. It's precisely the same process. And that's what makes this whole process so nice, because we do the same thing over and over and over again. All right, let's see. It's x squared then minus 3x. Kick out the existing constant by subtracting it on both sides. And now we want to identify this. We take half of that and square it. All right, half of 3. That's 1.5. How do we show that? Well, take half of it like this. Think of it as 3 over 2. See, that's half of 3. And it is the square of this that we're adding on both sides. So this is the amount that we're squaring on both sides. Now, when we get to the point where it becomes troublesome like this, it's arithmetically cumbersome, then I would do this. Now, half of negative 3, and I'm thinking of the negative involved here now, is negative 3 over 2. And so what we're doing is we're adding negative 3 over 2 squared. And on the right, we're adding negative 3 over 2 squared, but we'll expand it. And I'm leaving it factored here for the purpose of factoring in the next step. You see, identifying that binomial squared that we're going to have on the left side. Now, on the right, we want to go ahead and square this, and the squaring would give us, let's see, 9/4. So, on the right, we're adding 9/4. Now, it's important to realize that we could write this as 9/4 and go through the factoring process, but it turns out that it's a little easier if we just identify the amount being squared here, because when we go through the factoring, it's just simply x, then minus 3/2 without really thinking too much about it, and then all of our trouble has been shifted to the right side. We need to collect these two. This is minus 4/4. You see, 1 is 4/4 plus 9/4. Gee, negative 4 plus 9, that's 5, so this is 5/4 on the right side, collecting those two. Take your time with that sort of thing. I anticipated what was going to go on here. You might have to think about this a little bit, put in another step using common denominators and that kind of thing. But just don't make mistakes on the simple arithmetic with this. Take your time with that, slow down, and show all of the steps for that part of it. But the important thing that I'm trying to show you here is the technique that we're discussing here, which is completing the square. All right, then from here it is this x minus 3/2 is equal to plus or minus the square root of 5/4. And now x then is, add 3/2 on both sides, 3/2 plus or minus, let's see, the square root of 5/4 is the square root of 5 over the square root of 4. Now I want to write this in here, or think about it at least, in order to deal with this denominator. You know, we have the issue of rationalizing if we can't take care of getting that radical out of the denominator. So we have 3/2 plus or minus the square root of 5 over 2. And oh, look at this. In these two terms, we have common denominators, so we can bring these two together and write this as a single fraction. You see, it's 3 plus or minus the square root of 5 over the common denominator 2. And this is a more appropriate way to write the two answers. Now realize that this really is two answers in one. It's 3 plus the square root of 5 over 2, and the other answer is 3 minus the square root of 5 over 2. This problem involves another nuance, and the nuance is that the leading coefficient is not 1. It turns out that the method of completing the square only works, that is, this method of identifying the constant that completes the trinomial square only works, that is, taking half of that first degree term, half of the coefficient of the first degree term and squaring it, only works if the leading coefficient is 1. So we have to create that situation. And we can easily do it here by dividing through by 2. Now do notice also in this problem that on the left side we have no constant. The constant is already on the right. So it's kind of set up for completing the square at the front end. So here's what we're going to do. We're going to take the 2x squared and divide by 2 in order to clear that leading coefficient, to cause it to become 1. All right, and of course if we divide this term by 2, we have to divide every term by 2, so we're thinking like this. Now I'm going to leave a space for, you know, in this format of completing the square, we always leave a space here for the new constant term. And I'll create that space right here, but on the right we need to also divide by 2. Now let's burn another step to show what we have at this point. We have x squared minus. Now I'd like to show a distinct coefficient of x right here, and I can do that by writing this term as negative 1/2 x, you see, and then equals 1 on the right. Now my constant here that completes the trinomial square is found by taking half of this and squaring it. Half of that and squaring it. Well, let's take what we have. You see, all we need to do is just be very careful with it. Let's take what we have. Now let's take half of it. You see, and then what we're going to do is square that amount. You see, it's half of this squared is what we're showing here. And this is what we either need to think about or actively write down somewhere in order to get this right every single time. This becomes negative 1/4 squared, and negative 1/4 squared is positive 1/16. Now, it's 1/16 then that we're adding on both sides, but we would probably show it like this on the left side for factoring purposes. That is, we would think that this is plus this amount squared. Almost didn't leave myself enough room. And on the right, we'll write it as 1/16. All right, here we go. We can factor easily on the left side, and on the right we have a little arithmetic to do. So on the left we have, let's see, x, and then minus 1/4 squared. On the right, this is 16/16 plus 1/16, that's 17/16. And now we have the condition where we can use the this square root idea on both sides. We know then that x minus 1/4 is equal to plus or minus the square root of 17/16. And we're thinking of this as the square root of 17 over the square root of 16 so that we can simplify a little bit. X then is, I'm adding 1/4 on both sides, plus or minus the square root of 17 over the square root of 16, which is 4. And we have common denominators here, so we can write this as 1 plus or minus the square root of 17 all over the common denominator 4. And that would be our two answers in one. Here's another one, same idea. We have a leading coefficient that is not 1. We'd like to change it to where we have a leading coefficient of 1 and proceed from there. Now, at the same time, I'm going to kick out the existing constant term. Here's what we're going to do, whether we write this or not. We're thinking about kicking this over here and dividing through by 4. And we have to somehow accomplish that. I think the safe thing to do at this point is to actually write everything down. Just show a separate step for everything that we're doing. And then if we make a mistake somewhere along the line, we can always go back and find out where the mistake was made. All right, the 1 goes to the other side and becomes negative 1, and this becomes negative 1 over 4 as we divide through by 4. So we've got, let's see, the 4's go out here. We have x squared. Oh, this is nice. 8 over 4 is just 2, so we have minus 2x, vacancy, and on the right, negative 1/4. And now, to complete the square, half of 2 is 1. 1 squared is 1, so we're adding 1 on both sides. Over here, when we factor, x minus 1 squared. And on the right, let's see, 1 minus 1/4. Oh, that's 3/4. And let's see, then x minus 1 is plus or minus the square root of 3/4. So x then is 1 plus or minus the square root of 3 over 2. And we could leave it like this. This is a valid answer. Or we could write this as one fraction if we want to, thinking of this as 2 over 2. You see, we can think of this as 2 over 2 and write this as 2 plus or minus the square root of 3 over the common denominator 2. It's important to know that these are equivalent because you might get this on your paper and have this in the back of the book, and you have to be able to recognize that these are kind of interchangeable.